Good morning. So today we're going to complete the back page of the notes, which refers to the third question, which is how many solutions are there in a system? So we have three options. The first is one that we're used to. We would go in, we'd graph one line, we would graph our second line, and then we'd find, oh, there's an intersection point. That's our one solution. The other option, the second option, we saw at the end of yesterday, we went and graphed one line, and then we went to graph the other one, and we found out they never intersect because they're parallel, meaning there's no solution. And then the third option, we would go to graph our first line, and then when we go to graph the second line, we find out that they're the exact same line. And if the way we find our solutions is by looking for intersection points, it can intersect once, it can never intersect, or in this situation, if they're the same line, they're always intersecting at every single point, meaning there's infinite solutions. So let's go ahead and do a couple examples. So these say decide how many solutions each system has. We're not concerned with what the solution is, just how many there are. So if we start by graphing, whoops, I meant to use the highlighter. If we start by graphing this one, our slope is 2, our y-intercept is 4. So I'd start at 4 and go up 2 over 1. And then do the same thing in the opposite direction. Oh, and it looks like I didn't erase my green. That was kind of inaccurate. Let me fix that. There we go. But we'll do it in green since I already have that green there. This equation, we have a slope of -1 and a y-intercept of -3. So as I already have here, I start at -3 and then go down 1 to the right 1. Do the same thing in the opposite direction. And we graph. And now here, if we're looking for the intersection point, this is an ugly intersection point. And usually you won't see that. But the reason we're not concerned about that is because this is only asking us how many solutions are there. We don't need to know exactly what that point is. All we need to know is that there's only one point where they intersect. So one solution is our answer. Okay, so let's go on to the next one. Go back to my blue. So here we have a slope of 3, y-intercept of 2. So I'll start at 2, up 3 over 1, up 3 over 1. Do the same thing in the other direction, and graph. Okay, and then I'll do it this one in green again, but we can't just automatically say what our slope and y-intercept is. I introduced this to us yesterday. We have to do is solve for y, so we have to divide by 4 first before we can do anything. And get y equals 3x. Now it's in the formulaic, so now we can see we have a slope of 3, and there is nothing we're adding or subtracting, so our y-intercept is just 0. So we'll start at 0 and go up 3 over 1. And then I'm going to do the same thing in the other direction. Try to connect these points. These lines are very close. Oh, that wasn't super accurate. Let me try and move it over a little bit. Maybe. That's a little better. So I can't really tell what's going on here. It kind of seems like they might be parallel, meaning there wouldn't be an intersection point, but they're so close, and I don't know if my graphing's accurate. So what I'm actually going to do is show you a trick. If we just focus on the slope and y-intercept that we wrote down, we can see they have the same slope, but they have different y-intercepts. We didn't even need to graph this. we could automatically see from the information that these are the same, but the slopes are different, that they're going to be parallel lines, and there's going to be no solution. So if I come down to the next example, whoops, and I look and I'm like, how the heckaroo would I graph that? I couldn't. I couldn't go down to -16. So I don't even have to graph it. My slope of the first one is 4, but the slope of the next one is 10. If they have different slopes, just like the one above, they had different slopes, that means the angle at which these lines are traveling is different. One is steeper than the other. So conceptually, that means at some point in time, we don't know where on the graph, but somewhere on the graph, they're going to have to intersect with each other. The only way they wouldn't is if they were parallel, and these aren't parallel, for sure. They're not parallel, meaning they have to at least intersect once, but they have different slopes, so they couldn't intersect everywhere, meaning we're only going to have one solution. All right, so moving on to the next one. This one has, the top one has a slope of 3, a y-intercept of 2. The next one we actually have to do a little work for. We have to solve for y. So we have to add 6 to both sides. Get 2y equals 6x plus 4. Divide everything by 2. Get y equals 3x plus 2. Now it's in the form we like. So we can see that our slope is 3. Our y-intercept is 2. I feel like a broken record. Oh, that's because I just said the exact same thing. These two lines have the exact same slope and the exact same y-intercept. So if I were to graph them, I'd start at the same point and I would have the same slope, meaning they're the exact same line, telling us we have infinite solutions. All right, let's keep using that trick. But this one we have to actually fix both of our equations. So for this one, we'd have to subtract 4x, get 3y equals -4x minus 15, and then divide everything by 3, get y equals -4/3 x minus 5. So here, our slope is -4/3. Our y-intercept is -5. I'm going to do the other one. I'm going to do it in a different color. So we've got 5y equals 5x plus 10. This one's a little quicker. We already have the 5y by itself, but we just want y by itself, so we have to divide by 5. Get y equals x plus 2. So here we have a slope of 1, a y-intercept of 2, and if I just focus on my slopes and y-intercepts, and I don't have to graph, I first look at my slopes, and they're two completely different numbers, meaning the angles that these lines are moving at, again, are totally different. So they're not parallel for sure, meaning they're going to have to intersect exactly one time, one solution. All right, last problem. These look like they're almost the exact same equation, so I'm curious to see what happens when we solve each of them for y. So here we subtract 3x, get 2y equals -3x plus 10. Divide everything by 2, because we want that y by itself. And then this would be 5. So my slope is -3/2. My y-intercept is 5. And do the same thing again with the other one. Let's do blue this time. So 3x minus 2y equals 10. Subtract that 3x to the other side. You're left with negative 2y equals negative 3x plus 10. So you have to divide by negative 2 this time. Get y equals, those negatives will cancel for the negative 3 over negative 2. So we'll have positive 3 over 2x. And then 10 divided by negative 2 would be negative 5. So here we have a slope of 3/2 and a y-intercept of negative 5. And then if I just focus on my slopes and y-intercepts, I first look at my slopes, and they look similar, but they're different. As soon as you see that they're different slopes, every time, even though they look close, every time we can say one solution. So let's go back to the top and write our hints down so that we can remember them. So if there's one solution, that happens when we have different slopes. If there's different slopes, then we automatically know they're not parallel lines. They couldn't be the same line either, so they have to be one solution. No solution is if we had the same slope, saying that they're parallel, but we have different y-intercepts, and I'm just going to write different b. Then infinite solutions would be same slope, so same m, and same b, meaning they're the exact same line. All right. Have a good day.